This episode is brought to you by Brilliant. We've occasionally said that Jupiter, with its many moons, is practically a second solar system inside our own. But what if we could actually make Jupiter a second sun? In Arthur C. Clarke's classic novel 2010, the sequel to the legendary 2001 A Space Odyssey, Jupiter is turned into a second sun by mysterious alien benefactors, with the message bearing a gift and a warning. All these worlds are yours except Europa. Attempt no landing there. Use them together. Use them in peace. Since then, the notion that Jupiter might be turned into a sun has become a rather popular bit of science fiction speculation. Can it be done? Would it turn the Jovian moons into better sites for colonies? And what benefits or problems would it bring to Earth? We should start with the obvious. While Jupiter is enormous, roughly matching the combined mass of every planet, moon, and asteroid in the solar system, including the Oort cloud, Jupiter is still only 1,000th the mass of our Sun. You may have heard that Jupiter would need to be 80 times more massive to be a star, but the lowest mass star we found thus far that burns hydrogen, 2-mass JO523-1403, about 42 light-years away from us, is actually just 67 times more massive than Jupiter. Given that stars that small are the hardest to see, it is very unlikely that one coincidentally a mere 42 light-years away holds the record for least massive star, more likely that the galaxy contains some we can't see that are even lower. Of course, that only includes classic hydrogen-burning ones, not deuterium-burning stars or ones of an artificial nature, and we'll explore those options today too. There are many artificial routes by which one might be able to ignite Jupiter, some of which we spoke of in more detail in our episode Making Suns, but one might want to ask what the effect would be if we could do that. Generally, the larger a star is, the brighter. Doubling one's mass will make it about 10 times brighter, and the reverse is true too, half the mass, about 1/10 the brightness. This is only a rule of thumb rather than a smooth curve, but for instance, that tiny red dwarf 67 times more massive than Jupiter we mentioned a moment ago is quite dim, our own Sun being 7,200 times brighter, even though our Sun is only 16 times more massive than it is. We would expect a Jupiter star to be vastly less bright just following that mass curve, but if it were that bright, since Jupiter is 5 times farther from the Sun than Earth is, and usually 4 to 6 times farther from Earth than the Sun, we would expect it to be about 100,000 to 250,000 times less bright in our sky than our own Sun. And indeed actually a lot less to the naked eye, as far more of that light it would give off is in the infrared range, rather than visible wavelengths. As small as that number sounds, don't assume that wouldn't still be a very bright object. The Sun is 400,000 times brighter than the full moon, so such a star would parallel that, giving off more total light but a big chunk of it invisible to our eyes. Our eyes are logarithmic in nature, so we don't really notice changes in brightness as much. For instance, most of us would consider the lighting of a 10-watt LED bulb in a room quite bright, but would generally be only about 1,000th the light in that room that it would get if we ripped the roof off to expose the room to a cloudless noon sky. And indeed the light of the Sun out at Jupiter, 5 times farther from the Sun than us, and thus 5 squared or 25 times dimmer, is still brighter than most cloudy days here, and quite enough for all but the most sun-loving plants. What would the light be like on Jupiter's moons if it became a sun though? Jupiter has dozens of moons, but it's really the core 4, the Galilean moons of Io, Europa, Ganymede, and Callisto that generally interest us, as they each outmass the rest of the tiny moons combined, and approximate our own moon's mass and size. If we did make Jupiter into a star as bright as that dim and tiny red dwarf, then Io, the closest to Jupiter and 350 times closer to Jupiter than Earth is to the Sun, would be getting 17 times more light from that Jupiter star than Earth gets, while Callisto, 4 times farther away, would be getting about as much light as Earth does. That's a bit problematic because Io, for instance, is already rather warm from tidal heating by Jupiter. Which raises the other problem, tidal locking. All of Jupiter's moons are tidally locked to it, showing the same face to Jupiter as they orbit it. When most of the light they get comes from the Sun, this is not a big deal, as they aren't locked to our Sun and thus have day lengths the same as their orbital period around Jupiter, ranging from 1.8 Earth days on Io to 16.7 days on Callisto. The sides facing Jupiter always face Jupiter though, so if it was ignited into a star, only those sides facing Jupiter would get any of its light. Now they'd still be getting the sun's own light, which as mentioned is hardly trivial, more than your typical cloudy day, but it means your day-night cycles would be quite bizarre on those moons. On Io, for instance, one side would still only get the sun, with a 43-hour day-night phase, while the other side would have Jupiter burning overhead all the time, and our own sun meandering a bit more dimly across the sky for around a day than gone for around a day. Out at Callisto, the same would apply, only our sun would be putting in appearances for a bit over a week then disappearing for the same, as it has a 16.7 day orbital period. Incidentally, on Europa that period is 3.5 days, and Jupiter would be about half as bright as on Io, while on Ganymede that period is 7 days and 15% as bright as on Io. Not exactly setting us up for success in making nicely terraformable worlds. And most of Jupiter's moons are even farther away. There are 4 tiny ones that are closer than the Galilean moons, with Metis, the closest, orbiting every 7 hours, and it would get about 10 times more light than Io would, and nearly a couple hundred times more than Callisto. Jupiter's other 71 moons, at last count, are a good deal farther away, and indeed most have orbital periods of a year or more. Key notion here, before we discuss some of our options for making Jupiter a star, this doesn't exactly result in a new miniature solar system full of terraformable worlds, in any classic sense anyway, and that's before even remembering that these are not big places with lots of gravity. Again, the big 4 Galileans only roughly match our own moon. Now, why a star needs a certain mass to be a star, and why the bigger ones are exponentially brighter than the smaller ones, comes down to what makes fusion happen, or to be more accurate, what makes fusion happen more often. As I mentioned in our episode Fusion Power, it's actually rather rare even in our own sun, so much so that if you took a portable generator's volume of the sun and kept it magically under pressure, you'd be lucky to power a dim light bulb with that. That's the whole problem with making fusion reactors. It is not enough to replicate the sun's interior conditions, because the sun, for all its brightness, only generates about 1 watt of power for every 5 tons of its mass. Now for our sun, most of that takes place in a smaller fraction of the core, but for comparison, the biggest stars generate more than 20,000 times as much brightness per unit of mass, which is still only 4 watts per kilogram, akin to a flashlight in brightness and mass, while that tiny little red dwarf we were referencing is generating about 1 watt of light for a couple million kilograms of mass. If we could match that with Jupiter, it would still be 67 times dimmer and thus barely able to warm even Io, the closest of its big moons. Why this is the case all comes down to temperature and pressure. The more you squeeze a gas down, the hotter and higher pressure it tends to be, which essentially means random atoms inside it are moving around faster, making them more likely to bump neighbors, who are also more densely packed in too, thus even more likely to collide at any given moment. And because they are a higher temperature and thus moving faster, those are much higher energy collisions and more likely to cause a fusion event. It's still really rare even in the biggest stars, which still live a million years before having burned up a decent fraction of their hydrogen, and it's so rare in the smallest of stars that it takes them trillions of years to do that, meaning any given particle in the core undergoing a true fusion event will generally need a trillion years for that to be a likely event. Certain materials like deuterium are more likely to fuse when they strike, thus why you can have temporary deuterium burning in brown dwarfs, which can be thought of as either the very smallest of stars or the very biggest of planets if you prefer, but this is still minimal. Though it would be far higher if we made a star entirely out of deuterium, something we discussed in the episode I mentioned earlier, Making Suns. That pressure at the core of a star comes from all those upper layers pushing down on it, and all that gravity from that mass. However, that's not the only way to make pressure. You can't just squeeze an object down. Not as hard as it sounds like with a star either, as they generally have a low density. Indeed, our sun's surface, which is a pretty ambiguous concept, is a good deal less dense than our own atmosphere. We've often talked about making active support structures on this show, including giant spheres the size of Jupiter, what we call shell worlds or mega-Earths. And while that usually is constructed with the intent of holding mass above it, not inside it, the principle still applies. we could make a giant shell around Jupiter and start squeezing it down. If that shell were constructed of a high-temperature melting point material like tungsten, we might not even need to ignite fusion in Jupiter's core to get light out of it. Before we had cheap LED light bulbs, the most common sort was the incandescent bulb, which worked by running electricity through a tungsten filament inside a glass bulb. That really has nothing to do with electricity. Any given bit of wire has a resistance to electricity and heats up when you run current through it. We just used that current and resistance to heat up a long strand of tungsten till it glowed with its own contained heat and emitted light, same as a hot metal rod. Because it had such a high melting point, we could heat it up to temperatures that produced lots of light in the visible spectrum. Planets contain a stupid amount of potential energy from when they formed, as all that mass falling into them gained as much energy as it takes to lift something out of orbit, and it rises sharply with mass. Jupiter, while only 300 times more massive than Earth, has about 10,000 times the binding energy, about as much as the Sun produces in a couple centuries of its sunlight. As a reminder, the Sun's total illumination is a couple billion times more light than actually hits Earth from the Sun, since space is so huge, so that binding energy of Jupiter could illuminate Earth for 400 billion years if it was all concentrated on Earth. And remember, we're not even discussing fusion yet. If we compress Jupiter some more, its binding energy will actually increase as metal falls deeper down, and injects more potential energy as kinetic energy slamming around as heat. If you crunch Jupiter down inside a big tungsten globe, or some other high temperature material, it will heat that tungsten up till it glows red hot. Literally a giant light bulb, no different than the incandescent bulb most of us grew up with for interior lighting. And that would be a white light, same as those bulbs were, just a cooler, more reddish-orange tint than what we associate to sunlight or hotter spectrum LED bulbs. You slowly lose energy as that radiated heat and cooled, and so you need to keep crunching Jupiter down. But if your aim was to produce something about a 10,000th as bright as our Sun, you are looking at many thousands of years of illumination. Of course, while you're doing this, the core is getting compressed more, though in fact that's mostly metallic hydrogen and other heavier elements, but you'd probably be getting a good deal more fusion events. Note that I say more because there already is some. Hydrogen bumping around occasionally undergoes fusion, it's just way more often the more energetic the particles are, and the more frequent the collisions happen from packing them in tight together. Assuming you can keep ramping your pressure up in that core, you will get more fusion, and you can keep tightening your big globe down until that fusion is happening often enough to keep your big globe at super hot temperatures, but not actually melting, just glowing bright. Conceptually, this is very similar to how stars normally work too. They achieve a hydrostatic equilibrium as all the heat they produce tries to force particles further apart, while gravity tries to hold them together, and they equalize at a given radius where the uppermost layers are trying to fall down from gravity while heat is trying to push them apart. If the star collapses more, fusion rises, heating it and pushing the star wider, which lowers pressure in the core, decreasing fusion rates. This reaches a balance point based on stellar mass and composition, which again we call hydrostatic equilibrium. We're just cheating a bit by using a big metal globe to shove down. Now doing that takes a lot of power. Active support is not free, neither is keeping cool any parts you need not to be running hot. But there is a big power source available, obviously, and since all that energy expended eventually ends up as heat, which is our goal anyway, it hardly needs to be an efficient process. You can also potentially be doing this crunching magnetically. All that heat makes for a lot of ionized material after all, same as on a star, so you could potentially be crushing a star down by running a massive amount of magnets around it. You also don't necessarily need to be making Jupiter all that bright. As mentioned, most of our Sun's light meanders off into the void rather than hitting planets, and we can be using mirrors and lenses orbiting a planet or a star to focus a dimmer light onto a planet or moon in the quantity we want. This is a good way of solving both the issue of Jupiter's moons being at differing distances from it, and the issue of them having a dark side due to being tidally locked. You just put mirrors and lenses around your Jupiter star to focus light on those moons, and others out past that moon to reflect light onto their dark side. You don't even necessarily need to bother with regular orbits either. Such a mirror is essentially a solar sail, and that lets us play with orbital periods a lot, what we call statites and lagites, things with no orbital period or slowed orbital periods, by using a mixture of light pressure and gravity to define their orbital period rather than just gravity. For that matter, since those moons have little mass and gravity, space elevators work fine on them, and actually a good deal better if they're being used to tether a giant mirror at their top that your shiny and powerful light beam on to reflect on the surface below. That light pressure decreases the effective weight of the structure. Indeed, you could actually use that trick for space elevators around Earth, just having big mirrors fanning out around your tether as it ascended from ground to orbit, and bouncing light beams off them to hold them up, and either bouncing that light off or skipping the extra momentum of bouncing the photons in favor of absorbing them into big solar power collectors, whose power could run down that tether to be used as electricity ground side. This is effectively a lagite space elevator. I'm not sure it's the best approach to space elevators or power generation, but it's a notion I've played around with occasionally over the years and keep meaning to do an episode or aside on. Of course, if we're putting big mirrors and lenses around Jupiter, we might just want to do that directly around those moons and use our existing sun, but that would still work better around Jupiter in many ways because those mirrors are thin and Jupiter makes a good gravitational anchor to keep them from flying off, as they are solar sails, unless you add a lot of mass as ballast. That, incidentally, does not have to be a huge amount. Light pressure is pretty minimal, which is why solar sails need to be so thin. But if we're talking mirrors to move the sun's own light around the Jovian subsystem of moons, those don't necessarily need to be orbiting. Jupiter is huge, and we can float things in its atmosphere by regular orbit buoyancy. It's a mix of hydrogen and helium, and so pure hydrogen, refined out from that inside a big balloon, is lighter than the atmosphere and thus would float even better if we heated the content a bit. Jupiter's surface area is 120 times larger than Earth, so even though it only gets light from the sun at a fraction of Earth's intensity, it's still about 5 times as much total. Whereas the total surface area of all Jupiter's moons combined is a bit less than Earth's, Ganymede having the most at 17%. If you could start building tons of floating mirror platforms on Jupiter that bounce light at those moons, then you only need to cover a modest fraction of Jupiter's surface with them to keep those worlds nicely illuminated, and to the amount you want for each one, which might be a good deal less than Earth since these moons contain an awful lot of ice, and melting them might not be a great idea, at least initially or quickly. Speaking of floating things in Jupiter's atmosphere though, our main interest in Jupiter is usually in the context of a fusion economy, one running on some form of portable and compact fusion rather than stars or hypercompressed gas giants. If that ever took off, we'd probably have huge floating refineries on Jupiter and other gas giants sucking out hydrogen or deuterium, hydrogen's heavier and more easily fused isotope. Such a refinery would probably have a fusion plant on hand and be separating out the hydrogen, deuterium, and helium, and be venting hot helium from the bottom to provide lift, keeping hot hydrogen inside as a lifting gas, and filling tanks of deuterium up as its export. You don't necessarily need very good artificial fusion to want to use this approach either. Hydrogen, deuterium, and helium all have a lot of value, and in a case like that you might simply use beamed energy or lasers generated closer to the sun to power such floating refineries. As we mentioned in colonizing the sun, it's actually fairly easy to make giant lasers in the sun's upper layer by using a pair of big mirrors, and that atmosphere as your lasing medium between them. There's any number of materials that could handle being mirrors in the sun's upper atmosphere, though they'd wear down with time, but they are cheap to make. We call these stellasers, and they can be built big or small, and easily keep a beam on target anywhere inside our solar system. Interesting thing about lasers is that they are just a pair of mirrors and a medium that gets excited by light and gives off light, usually some gas which is abundant in the atmosphere of not just the sun but gas giants too. So not only can you just pour lasers down on Jupiter to heat it up, but you could also turn it into a giant fluorescent light bulb, as hydrogen and the other gases in Jupiter's atmosphere do have excitation frequencies in the visible spectrum. More importantly though, if you're using stellasers a lot, you can create large laser highways throughout the solar system and between stars, as we looked at in Interstellar Laser Highways, allowing very fast and cheap spaceship travel. You generally need places to dump momentum though, as that has to be conserved and pushes your mirrors around, so it helps to have large massive objects to dump momentum into. You can place Meteors in deep space, being hit by lasers, but they will move, and while you can bounce them off each other, you do need to cement any given relay of Meteors with heavy endpoints, and planets, especially giant ones like Jupiter, are great for this, as even whole armadas of massive ships could ply the space lanes for millennia while barely nudging such giants. The connection doesn't have to be physical either, as you can dump into orbital Meteors gravitationally bound to the world with a little extra effort. And those are likely to scatter a lot of light, another way you might make them into a second sun. Indeed, of all the scenarios we discussed, this one seems the most probable, that you'd be using Jupiter and the other gas giants as large hubs of interplanetary and interstellar laser highways, with some of the light diverted from surplus Meteors to reflect on those moons and artificial habitats built in orbit or to power other light sources, particularly if we don't achieve useful fusion in the future. We often assume only with artificial fusion can we ever truly conquer the solar system and stars beyond, but in truth, while it might slow down expansion waves who'd have problems slowing down on the approach to uninhabited regions using pushing lasers, once those are in place, we can use existing suns to more than easily power solar economies, both the colonies themselves and the ships venturing around inside them or between other inhabited systems. Of course, if you have artificial fusion, trying to make artificial stars is less necessary. It also probably opens up some routes to turn the planet into a star a lot easier, like some version of the magnetic compression technique we mentioned a while ago, in which case you could easily run lighting on Jupiter from the surplus of those gas refineries and extraction spots sending fusion fuel off to the colonies. But you might decide what you really want from Jupiter is to get all that gas off. It has plenty of value all on its own even without fusion economies, and you might decide it's easier stored and handled by being removed to smaller storage depots, where it serves a function as shielding or mass even when not in use. But more importantly, hydrogen and helium are incredibly common throughout the universe, being rare only in the warm inner solar system where virtually all of it is in the sun and the remainder is mostly tied up in Earth's oceans and crust. However, deep down under Jupiter's layers, we get to metallic hydrogen, which might be extractable and make a nice fuel itself, and below that is more rocky material, stuff like carbon and iron and gold and platinum, probably more than all the rest of the planets combined. If you strip that gas off, you get access to all of it. We're not quite sure how much metal is inside Jupiter. It is hard to calculate, and indeed we think it may have been hit early in the solar system's formation by a planet 10 times Earth's mass. There were a lot more planets and protoplanets and dwarfs in the early days, we think, which consolidated into the current ones. However much it is a huge amount of material we'd want, and if we have fusion, we could boil it off by using fusion candles, essentially giant two-way fusion rocket flames. See colonizing Jupiter for more discussion of those, and mass export of gas to fuel fusion economies elsewhere. Without it though, if we want it fast, we can just torch Jupiter by Death Starring it with mass to laser fire, and remove that layer by evaporation and magnetic extraction, akin to the process discussed for removing mass from the Sun in the episode Starlifting. This is not a fast process. As I said earlier, the gravitational binding energy of Jupiter is equal to 200 years of solar output, so even if you were directing all that light from the Sun and Jupiter, it would take that long to burn it all off, and obliterate all the Jovian moons as the place would be literally turning into a second sun and not a tiny dim one. If on the other hand, you were trying to slowly remove it, applying something more akin to what we contemplated when discussing replacing Jupiter with the smallest known red dwarf, it would take a good deal longer, more like a couple million years, during which time Jupiter would glow quite brightly, and that would only use up about 1% of 1% of the sun's output. When you're done, you've got all that raw material, but it is a slow process. This also works on the other gas giants, and indeed is a good deal easier and faster as they have far less binding energy, but that is certainly one way to make summer on Jupiter, and when you're done, you have a rather large rocky planet left behind, though you'd have to wait for that to cool of course, but I suppose that would be autumn on Jupiter. So we were talking today about making stars by artificial means, and if you're curious about stellar formation and star life cycles, there's a number of good discussions and quizzes on the life cycles of stars in Brilliant's astronomy course, which covers everything from the basics to fairly advanced concepts, and does so in a fun and interactive fashion. In a time when more folks are embracing online education, Brilliant's focus on fun and interactive methods makes them a great choice, whether you're a student, a parent trying to enhance your kid's education, a professional brushing up on cutting-edge topics, or someone who just wants to use this time to understand the world better. You should check out Brilliant. Try adding some learning structure to your day by setting a goal to improve yourself, and then work at that goal just a little bit every day. Brilliant makes that possible with interactive explorations and a mobile app that you can take with you wherever you are. If you are naturally curious, want to build your problem-solving skills, or need to develop confidence in your analytical abilities, then get Brilliant Premium to learn something new. Brilliant's thought-provoking math, science, and computer science content helps guide you to mastery by taking complex concepts and breaking them up into bite-sized, understandable chunks. You'll start by having fun with your interactive explorations. Over time, you'll be amazed at what you can accomplish. If you'd like to learn more science, math, and computer science, and want to do it at your own pace and from the comfort of your own home, go to brilliant.org/IsaacArthur and try it out for free. So we have a fun schedule coming up for the rest of June, starting next week with a return to the Fermi Paradox, to contemplate what it would be like to be the first civilization to arise in the galaxy, and if we might be such a civilization ourselves, in the Fermi Paradox Firstborn. Some folks have suggested the oldest civilization in a galaxy full of aliens might tend to act as a police force on the others, and 2 weeks will examine that notion, as well as how we might engage in bringing law and order to distant off-world towns in space, in Space Police. And in 3 weeks we'll take a look at graphene, what it is and what we might use it for, and how this super strong material might impact our civilization. For alerts when those and other episodes come out, make sure to subscribe to the channel. And if you enjoyed this episode, hit the like button and share it with others. And if you'd like to support future episodes, you can support the show on Patreon or visit our website, isaacarthur.net, to donate to the channel, see our list of episodes or book recommendations, or buy some awesome SFIA merchandise. Until next time, thanks for watching, and have a great week.